In this video, I'm going to talk about isomers, a little bit about isomers, and then focus on constitutional isomers. And then we would learn how to name these molecules using IUPAC nomenclature. Let's start with isomers. So isomers are compounds that have the same molecular formula but are structurally different. So these are compounds that have the same molecular formula but are structurally different. That's what isomers are. Now, isomers are broadly divided into two types: constitutional isomers and stereoisomers. Stereoisomers, again, are of different types, but my focus today would be discussing what constitutional isomers are, and then we are going to use these type of isomers to learn how to name organic compounds. So we would just be focusing on constitutional isomers for this lecture. I would do a separate recording for the different types of stereoisomers. Now, what are constitutional isomers? Just like isomers, like the general definition of isomers, the first point has to be valid, that these are compounds that have the same molecular formula. So constitutional isomers are compounds that have the same molecular formula. However, their bonding pattern is different. However, their bonding pattern is different. Let's look at an example. So I am going to give you the molecular formula of C2. So molecular formula C2H6O. So I'm going to make compounds that have 2 carbons, 6 hydrogens, and 1 oxygen. So for the first one, let's do this. Let's draw a carbon-carbon-oxygen bond. That would be my backbone of the molecule. For the other one, let's draw a carbon-oxygen-carbon bond. Now the rest of it, I'm going to just fill up with hydrogens as required following octet rule. So my first carbon already has a bond, needs 3 more, and all of these are hydrogens. The second one has 2 bonds. We know carbon likes to make 4 bonds when it's neutral, so the rest 2 must be with the hydrogens. And then oxygen in its neutral state likes to make 2 bonds. One was already there, so the other one must be with the hydrogen. For the second compound, my first carbon needs 3 more bonds, each with hydrogens. Oxygen does not need anything more. It already has 2 bonds. And the last carbon also needs 3 bonds with the hydrogens. Now you can see I used 2 carbons for each of these, 6 hydrogens for both of them, and then 1 oxygen. So molecular formula is same for both, but the bonding pattern is completely different. In organic chemistry, and I would do a separate lecture for this part as well, a COH type of linkage goes by the name of an alcohol. So this molecule is an example of an alcohol. Again, in organic chemistry, a COC type of linkage goes by the name of an ether. So this molecule is an alcohol. This molecule is an ether. Now we know alcohols and ethers are completely different molecules with completely different features and characteristics. For the alcohol type of molecules, just using your knowledge of general chemistry, which you probably have taken before organic chemistry, you know that this part of the molecule shows hydrogen bonding type of interaction. So let me move to a different page so that I can write this down for you. An alcohol molecule has this COH type of bond, and this is the part that is responsible for hydrogen bonding type of interaction. An ether molecule does not have an OH type of bond directly present in the molecule. Instead, there is a COC type of bond, and this type of bond is responsible for a dipole-dipole type of interaction. Do mention in the comments if you want me to do a video that talks about hydrogen bonding versus dipole-dipole and all the other type of interactions, and I'll be happy to do it for you. The best way to spot a hydrogen bonding interaction is remember that hydrogen always likes to have fun. Instead of FUN, spell it as a FON. So a hydrogen that's present with a fluorine or an oxygen or a nitrogen would show hydrogen bonding type of interaction. This was how I was taught it. And it's a really good way to remember. So hydrogen bonding interactions are stronger. Now, to be able to break these interactions, you would have to heat the molecule more. So a molecule that has a hydrogen bonding type of interaction should have higher boiling point. A molecule that has dipole-dipole type of interaction, which is weaker than a hydrogen type bonding type of interaction, must have lower boiling point. Just a little review of what you learned in general chemistry and how it's going to be extremely important to remember these things in organic chemistry. Now, I'm going to get rid of this paper and we would start talking about IUPAC nomenclature. So I am going to draw one molecule and then we would try to draw the constitutional isomers of those molecules and try to name them as well. So the molecule that I would start with goes by the name of hexane. And we would be focusing on the constitutional isomers of hexane. Okay. Now we know a molecule that's 1 carbon long goes by the name of methane. 2 carbons long would be ethane. 3 carbons long was propane. 4 carbons long, butane. 5 carbons long would be pentane. So hexane, as in hexa, alkane, must be 6 carbons long. So I am going to draw 6 carbons and then fill out the rest with hydrogens. So this needs 3, this needs 2, 2 more here, 2 more here, 2 more here, and 3 more here. And this is your hexane molecule. It's an alkane. All parts of this molecule just is made up of CC single bonds. So I know it's an alkane. And there are 6 carbons involved. So this is a hexane. We'll start learning IUPAC nomenclature from the second constitutional isomer. This one is a little too simple to see the variety of things involved in IUPAC nomenclature, but come the second one, we would realize it better. All right. Now, one thing that you should know is the first point of IUPAC nomenclature is to find out the longest carbon chain that is in a continuous pattern. So longest carbon chain in a continuous pattern is your parent carbon chain. So what that means is, if instead of drawing it all in a straight line, what if I had drawn this molecule this way? If I had drawn this molecule out this way, or if I had drawn this molecule out as 4 carbons in a line and then 2 others hanging from there, all of these versions of your molecule would still be called a hexane, because the longest carbon chain in a continuous pattern would still be 6. 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. So you could draw this in a variety of ways. I could draw 2 carbons or 3 carbons this way, 1, 2, 3, 4, 5. And then I could draw 1, 2, 3, 4, 5, and 6. It would still be called hexane, since I have 1, 2, 3, 4, 5, 6, all in a row. And that is my longest carbon chain. So these are all same as the above drawn molecule, same as the above drawn molecule. So there's absolutely no difference between this and either one of these. So these are not considered as constitutional isomers of that. It is the same thing. Now, what would be a constitutional isomer? I could make a constitutional isomer if I would draw 5 carbons in a row and place the 6th carbon somewhere else. So my first constitutional isomer would be, instead of putting 6 carbons in a continuous pattern, I would go ahead and put 5. 1, 2, 3, 4, 5. And I cannot put the 6th one here or here, because that would again make it a continuous chain. I need to make the chain 5 carbons long, the main chain, and then kind of hang my 6th carbon somewhere else where there is a loss of continuity. So I would move 1 carbon away from the side and put my 6th carbon here. Now my longest carbon chain is 1, 2, 3, 4, 5 carbons long. So the first rule of IUPAC nomenclature is to find out what is the parent carbon chain. So for this one, the parent carbon chain is a pentane, because it's 5 carbons long. Now, the last part of your name is the identity of your molecule, is the name of the parent chain of your molecule. So last part of the name is the parent chain of the molecule. So the name here would end in pentane, and I would come back and fill out the first part of the name in a second. Now I know this carbon already has 1 bond, so it must have 3 other hydrogens. I know this carbon has 2 bonds already, so it must have 2 other hydrogens. This also should have 2 more hydrogens. This should have just 1 more hydrogen because it already has 3 carbon bonds. The last one should have 3 more hydrogens, and then this carbon should have 3 more hydrogens as well. Now, when I said the name pentane, I only accounted for this part of the molecule. I haven't said anything about the CH3 that's hanging on to one of the carbons. Now, the part of your molecule that did not fall within the longest carbon chain is known as a substituent. So your CH3 group here is a substituent. that is the part that is hanging on to the parent chain. So I would just do it for the first one. This is the part that is a substituent, and then this is the part that is your parent molecule. Now, when I said pentane, I only accounted for the parent chain. I have to also include the CH3 part in the name. Now, to name substituents, you have to first number your parent chain. So you would spot your substituent and number your parent chain in a way that your substituent gets the lowest possible numbering. So number your parent chain in a way that your substituent gets the lowest possible numbering. So for this molecule, I could have either started from this end as carbon 1, or I could start from that end as carbon 1. If I start from this end as carbon 1, then my substituent would be at carbon 2. If I would have started from this end as carbon 1, my substituent would be at carbon 4. It is lowest possible numbering. So I would have to start counting here. This is carbon 1, 2, 3, 4, and 5. Now, you would also have to mention what is the substituent. So I know my substituent is at carbon 2, but my name also needs to specify what is the type of substituent that is hanging on to carbon 2. Now, if your alkane is a substituent, the naming rule says that the name of the alkane will change from ANE to YL. For example, what group do I have here? My substituent here is 1 carbon long. So ideally should have been called a methane. Ideally, it should have been called a methane. However, it is not the parent chain anymore. It is a substituent that's hanging onto a parent chain. So I had to remove 1 hydrogen from my methane to make room for it to be able to hang on to the parent chain. So when your alkane is behaving as a substituent, name changes to YL. So methane would now be called methyl. Methyl. So let's go back to the part that we were naming the molecule. The last part of the name is a pentane. The first part of the name should tell you the number of the carbon that your substituent is attached to, which is carbon 2. And then it should tell you the identity of the substituent. So 2-methylpentane. So last part of a name is your parent chain. And then first part of the name goes by substituent position, which is what carbon it is attached to, a little hyphen, followed by substituent identity. And then the rest of the name is your parent chain. So this was the first constitutional isomer of hexane, which is no longer a hexane, but it still has 6 carbons and the same number of hydrogens as a hexane would have. What else could we have done to make the next constitutional isomer? Well, we can still keep it 5 carbons long. So 1, 2, 3, 4, and 5. And instead of putting my CH3 on a second carbon, we could do it on the 3rd carbon, and that would change the name. So now my first carbon has 3 hydrogens. Second carbon here has 2. This has 1 more hydrogen. This has 2. And this has 3 hydrogens. And this carbon would have 3 hydrogens as well. Now, we know the longest carbon chain is 5 carbons long in a continuous pattern. Next up, we need to number. You could number from the right or the left. Either way, it's going to be carbon 3 that has your methyl group attached to it. So it doesn't matter. 1, 2, 3, 4, and 5. So what was again the way of writing these names? I would have to start with the position of the substituent. So 3, carbon 3 has a methyl group that is attached to it. And then the main carbon chain is a pentane. So 3-methyl pentane. I could also draw a few more. Well, I cannot move my methyl here. If I did, it would be the same as the previous one, because then I would start numbering from this side, and that would be the same as doing the 2-methyl pentane all over again. I don't want to do a repetition of what I have done before. My constitutional isomers should look new every time and should have a different name. We could make the longest carbon chain 4 carbons long instead of 5. And I could attach the rest 2 carbons both to the same carbon and then fill out the rest with hydrogens. This needs 3, this needs 2, this does not need any, this would need 3, 3 here, and 3 here. So I still have 1, 2, 3, 4, 5, and 6 carbons, and the number of hydrogens would match with the constitutional isomers that we have just drawn. My longest carbon chain is now a butane. I also have to number in a way that my substituents get the lowest possible numbering. So I could do carbon 1, carbon 2, carbon 3, carbon 4, and then we would have to write down the name. So at carbon 2, I have 2 methyl groups. Now, IUPAC nomenclature requires you to write down all substituents present in that position. So you would have to tell that at 2, you have 2 of these methyl groups that are present. So the first part of the name, again, is the substituent position. So you would say 2, comma, 2. So twice at carbon 2, I have 2 methyl groups, 2,2, dimethyl butane. Substituent position, what type of substituent, and then the parent carbon chain. Even though both are attached to carbon 2, you still have to mention it 2 times, 2, 2. Even though it's the same group, you still have to mention that it's dimethyl. It's 2 of the same groups. So the whole goal is, if I did not have this picture drawn, if you just had given me the name, I should be able to look at the name and draw the picture exactly how you want it to be. So I need all information required to be able to draw the correct picture. Now, one last constitutional isomer would still be 4 carbons long. Instead of putting both the methyl groups on the same carbon, I would just attach them to different carbons. You could do it on the same side, you could do it on different side. Name would still be the same. Fill out the rest with hydrogens. This needs 3, this needs 1, this needs 1, 3 here, 3 here, and 3 here. Longest carbon chain is a butane. Number it in a way that your groups, that your substituents get the lowest possible numbering. You either way, it would be 2 and 3. So you number it, number 1 here, 2, this could be my 3, this could be my 4. So I would have methyls at carbons 2 and 3. If I started numbering here, I would still have the same groups at carbons 2 and 3. So this molecule would be called 2, 3, because those are my substituent positions. dimethyl butane. So these are the constitutional isomers of hexane. You can always come up with your own alkane, maybe a pentane or a heptane, and try to draw different backbones, different parent carbon chain, and put substituents in different position and see what type of constitutional isomers you would end up with. And that would give you a very good practice with constitutional isomerism as well as IUPAC nomenclature. If you feel like these molecules could be drawn some other way, for example, instead of putting the two CH3s here, what if I change the position of my CH3s both to the first carbon or that carbon? You could try all of those yourself and try to name the molecule. Once you name the molecule, you will realize it's one of the molecules that we have already drawn. So these are the only isomers of hexane that you can draw. Anything else that comes to your mind, feel free to draw it out, name it, and you would see it's possibly a repetition of what we have already done. But that would give you a really good practice of drawing constitutional isomers and naming them. Thank you.